NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video. Today, we'll solve a problem about comparing two expressions with cube roots. Let's determine which of the given numbers is larger. Let's first see what expressions we need to compare. We have a equal to the cube root of 3 and b equal to the cube root of the cube root of 2 minus 1 multiplied by the cube root of 2 plus 1. To compare these numbers, we'll raise both a and b to the third power. This approach will help us eliminate the cube roots and make the comparison easier. Let's start with a cubed. A cubed equals the cube root of 3 cubed. When we raise a cube root to the third power, we get the original number inside the cube root. So a cubed equals 3. Now, let's calculate b cubed. B cubed equals the cube of our expression for b. We can rewrite this as b cubed equals the cube root of 2 minus 1 raised to the power of 1 times the cube root of 2 plus 1 raised to the power of 3. Now we need to expand the bracket, the cube root of 2 plus 1 raised to the power of 3. When we expand this, we get the cube root of 2 minus 1 multiplied by 2 plus 3 times the fourth root of 4 plus 3 times the cube root of 2 plus 1. Let's simplify this expression further. We can rewrite it as the cube root of 2 minus 1 multiplied by 3 plus 3 times the cube root of 4 plus 3 times the cube root of 2. When we multiply this out, we get 3 times the cube root of 2 plus 3 times the cube root of 8 plus 3 times the cube root of 4 minus 3 times the cube root of 4 minus 3 times the cube root of 2. Now, let's simplify by canceling like terms. The cube root of 8 equals 2. And the 3 times cube root of 2 terms cancel out, as do the 3 times cube root of 4 terms. So we have b cubed equals 3 times the cube root of 8 minus 3. Since the cube root of 8 equals 2, we get b cubed equals 3 times 2 minus 3, which equals 6 minus 3, which equals 3. Now we can compare a cubed and b cubed. From our calculations, a cubed equals 3 from result I, and b cubed equals 3 from result. Therefore, a cubed equals b cubed, which means a equals b. So the answer is that these two numbers are equal. Welcome to this mathematics video on comparing large exponential numbers. Today we'll solve a problem that involves comparing two numbers with large exponents. Let's look at our example. We want to find which of these numbers is larger, a equals 31 to the power of 11, or b equals 17 to the power of 14. At first glance, this might seem challenging because we're dealing with very large numbers. Let's solve this step by step following a strategic approach. First, let's start with a equals 31 to the power of 11. Let's analyze what we've done. We know that 31 is less than 32, so when we raise both to the power of 11, the inequality stays the same. We can rewrite 32 as 2 to the power of 5, and when we raise this to the power of 11, we get 2 to the power of 55. So now we've converted a to a power with base 2. Now that we have a in the form of a power of 2, let's continue by comparing this to the next power. We have 2 to the power of 55, which is less than 2 to the power of 56. We can rewrite 2 to the power of 56 as 2 to the power of 4 to the power of 14, which equals 16 to the power of 14. Now let's compare the powers of 16 and 17. We know that 16 is less than 17, so when raised to the same power of 14, the inequality remains. Therefore, 16 to the power of 14 is less than 17 to the power of 14. Now, we can write the final comparison. We've shown that 31 to the power of 11 is less than 17 to the power of 14. And since 17 to the power of 14 is equal to b, we can conclude that a is less than b. Let's recap what we've learned. To compare numbers with different bases and large exponents, we can convert them to a common base or create a chain of inequalities. Today we'll solve a mathematical problem involving comparison of two fractions with large exponents. Let's see which of the two fractions is larger. Let's look at our example. We need to determine which of the following two fractions is larger. A equals 19 to the power of 1998 plus 1. Divided by 19 to the power of 1999 plus 1, and b equals 19 to the power of 1999 plus 1, divided by 19 to the power of 2000 plus 1. Let's solve this step by step following a specific algorithm. For step 1, let's introduce a substitution to simplify our expressions. If we let n equal 19 to the power of 1998, we can rewrite our fractions as follows. A becomes n plus 1 divided by 19 times n plus 1. And b becomes 19 times n plus 1 divided by 19 squared times n plus 1. This substitution makes our expressions much more manageable. For step 2, we'll compare the two fractions by cross-multiplication. We want to determine whether a is greater than b. So we need to check if n plus 1 divided by 19n plus 1 is greater than 19n plus 1 divided by 361n plus 1. To compare fractions, we cross-multiply. This means we multiply the left-hand numerator with the right-hand denominator and compare that to the product of the left-hand denominator and the right-hand numerator. This gives us n plus 1 times 361, n plus 1 is greater than 19n plus 1 times 19n plus 1. For step 3, we'll expand both sides of the inequality. Let's start with the left side. We multiply n plus 1 times 361n plus 1. Using the distributive property, we get 361n squared plus n plus 361n plus 1. This simplifies to 361n squared plus 362n plus 1. Now for the right side. We need to square the expression 19n plus 1. Using the formula for the square of a binomial, we get 361n squared plus 2 times 19n times 1 plus 1 squared. This simplifies to 361n squared plus 38n plus 1. For step 4, we'll subtract common terms from both sides of the inequality to simplify it further. We have 361n squared plus 362n plus 1 on the left side, and 361n squared plus 38n plus 1 on the right side. Notice that the terms 361n squared and the constant term 1 appear on both sides, so they cancel out. After subtracting these common terms, we're left with 362n is greater than 38n. We can further simplify by subtracting 38n from both sides, giving us 324n is greater than 0. For step 5, we reach our conclusion. We've determined that 324n is greater than 0. Since n is equal to 19 to the power of 1998, it's clearly a positive number. Therefore, the inequality 324n greater than 0 is definitely true. Going back to our original question, this proves that a is greater than b. In other words, the first fraction is larger than the second one. Welcome to our math lesson. Today, we're going to solve an interesting comparison problem involving radical expressions. Let's start with our example. We need to determine which of the following numbers is larger. A equals square root of 1998 plus square root of 2000, or b equals 2 times square root of 1999. To solve this problem, we'll use an algebraic approach. Let's substitute n equals 1999 to make our calculations more manageable. So a becomes square root of n minus 1 plus square root of n plus 1, and b becomes 2 times square root of n. To compare these expressions, we'll square both sides. Let's start with a. When we square a, we get a squared equals open parenthesis square root of n minus 1 plus square root of n plus 1 close parenthesis squared. Now we can expand this expression using the square of a binomial formula. A squared equals the square of the first term, which is n minus 1 plus 2 times the product of the terms, which is 2 times square root of n minus 1 times square root of n plus 1, plus the square of the second term, which is n plus 1. Let's simplify this expression. The first term is n minus 1. The last term is n plus 1. When we add these, we get 2n. For the middle term, we can simplify what's under the square root. N minus 1 times n plus 1 equals n squared minus 1. Now let's find b squared. b equals 2 times square root of n, so b squared equals 4n. Now we can compare a squared and b squared. We have a squared equals 2n plus 2 times square root of n squared minus 1, and b squared equals 4n. To determine which is larger, let's examine the relationship between a squared and b squared. Let's set up an inequality to determine which is larger. We'll start with the inequality a squared is less than b squared. If this is true, then a is less than b, since both expressions are positive. Substituting our expressions, we have 2n plus 2 times square root of n squared minus 1 is less than 4n. Rearranging this inequality, we get 2 times square root of n squared minus 1 is less than 4n minus 2n, which simplifies to 2n. Dividing both sides by 2, we get square root of n squared minus 1 is less than n. Squaring both sides, we get n squared minus 1 is less than n squared. Simplifying further, we get negative 1 is less than 0. This is always true. Since this inequality is always true, we've proven that a squared is less than b squared, which means a is less than b. Therefore, b is greater than a. In other words, 2 times square root of 1999 is greater than square root of 1998 plus square root of 2000. Welcome to this math tutorial, where we'll solve a system of equations. Let's work through this step by step, following the solution process shown in our problem. The first step in our solution is to establish some inequalities. Let's look at the first equation. A to the power of 4 plus 14 of plus 1 equals n to the power of 4. We can show that n to the power of 4 is greater than a to the power of 4, which implies that n is greater than a. Since n is greater than a, we can also say that n is greater than or equal to a plus 1. This means that n to the power of 4 is greater than or equal to a plus 1 to the power of 4. Similarly, for the second equation, we can derive that m to the power of 4 is greater than b to the power of 4, which implies that m is greater than b. Since m is greater than b, we can also say that m is greater than or equal to b plus 1, which means m to the power of 4 is greater than or equal to b plus 1 to the power of 4. For the third equation, we follow the same pattern. We can show that k to the power of 4 is greater than c to the power of 4, which means k is greater than c. Since k is greater than c, we have k is greater than or equal to c plus 1, which implies k to the power of 4 is greater than or equal to c plus 1 to the power of 4. Now, we can substitute these inequalities back into our original equations. Here's our system again. A to the power of 4 plus 14 of plus 1 equals n to the power of 4b to the power of 4 plus 14bc plus 1 equals m to the power of 4c to the power of 4 plus 14ac plus 1 equals k to the power of 4. From our first inequality, we know that n to the power of 4 is greater than or equal to a plus 1 to the power of 4. So from the first equation, a to the power of 4 plus 14 of plus 1 is greater than or equal to a plus 1 to the power of 4. Let's expand the inequality for the first equation. We have a to the power of 4 plus 14 of plus 1 is greater than or equal to a plus 1 to the power of 4. When we expand a plus 1 to the power of 4, we get a to the power of 4 plus 4, a cubed plus 6, a squared plus 4, a plus 1. So our inequality becomes a to the power of 4 plus 14 of plus 1 is greater than or equal to a to the power of 4 plus 4, a cubed plus 6, a squared plus 4, a plus 1. Simplifying, we can subtract a to the power of 4 and 1 from both sides, getting 14 is greater than or equal to 4a cubed plus 6, a squared plus 4a. We can factor out a from the right side of the inequality. This gives us 14 is greater than or equal to 4a times a squared plus 6a over 4 plus 4 over 4. Simplifying the fraction, we get 14 is greater than or equal to 4a times a squared plus 3a over 2 plus 1. Finally, we can further simplify to 14 is greater than or equal to 4a times a squared plus 3a over 2 plus 1. Now, let's divide both sides by, assuming a is positive. We get 14b is greater than or equal to 4 times a squared plus 3a over 2 plus 1. Simplifying again, we get 14b is greater than or equal to 4a squared plus 6a plus 4, or 7b is greater than or equal to 2a squared plus 3a plus 2. Following the same steps for the other equations, we can derive similar inequalities. For the second equation, we get 7c is greater than or equal to 2b squared plus 3b plus 2. And for the third equation, we get 7a is greater than or equal to 2c squared plus 3c plus 2. So our system of inequalities is 7b is greater than or equal to 2a squared plus 3a plus 2, 7c is greater than or equal to 2b squared plus 3b plus 2, 7a is greater than or equal to 2c squared plus 3c plus 2. Now, let's add these inequalities together. Adding the left sides, we get 7b plus 7c plus 7a. Adding the right sides, we get 2a squared plus 3a plus 2b squared plus 3b plus 2c squared plus 3c plus 2. Combining like terms, we have 7a plus b plus c is greater than or equal to 2a squared plus b squared plus c squared plus 3a plus b plus c plus 6. Subtracting 3a plus b plus c from both sides, we get 4a plus b plus c is greater than or equal to 2a squared plus b squared plus c squared plus 6. Rearranging, we have 2a squared plus b squared plus c squared minus 4a plus b plus c plus 6 is less than or equal to 0. We can further simplify this expression. Let's factor out 2, getting 2 times a squared plus b squared plus c squared minus 2a minus 2b minus 2c plus 3 is less than or equal to 0. Rearranging the terms inside the parentheses, we can write a squared minus 2a plus b squared minus 2b plus c squared minus 2c plus 3 is less than or equal to 0. We can complete the squares for each variable. For a, we have a squared minus 2a plus 1 minus 1. Similarly for b and c. So our expression becomes a minus 1 squared plus b minus 1 squared plus c minus 1 squared is less than or equal to 0. Since squares are always non-negative, the sum of squares can only be less than or equal to 0 if each square is exactly 0. This means a minus 1 squared equals 0, b minus 1 squared equals 0, and c minus 1 squared equals 0. Therefore, a equals 1, b equals 1, and c equals 1. Now, let's verify our solution by plugging these values back into our original system. For the first equation, a to the power of 4 plus 14 plus 1. That's 1 to the power of 4 plus 14 times 1 plus 1, which equals 1 plus 14 plus 1, which is 16. This should equal n to the power of 4. So n to the power of 4 equals 16, which means n equals 2. Similarly, for the other equations, we get m equals 2 and k equals 2. So our final solution is a equals 1, b equals 1, c equals 1, n equals 2, m equals 2, and k equals 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.